A moon the size of Arizona is shooting water into space right now. Not metaphorically. Literally spraying massive plumes of liquid water hundreds of kilometers above its frozen surface. And we've been watching it happen for nearly 2 decades. Yet somehow, most people still don't know that Enceladus exists, let alone that it might be harboring life beneath its icy shell. That's about to change, because recent discoveries have transformed this tiny world from a curiosity into what might be the single most important place in our solar system. Enceladus orbits Saturn, tucked away in the outer reaches where sunlight is 100 times weaker than on Earth. At first glance, it's nothing special. Just another ice-covered rock barely 500 kilometers across, small enough to fit inside the borders of Texas. But in 2005, the Cassini spacecraft flew past and spotted something that made absolutely no sense. Jets of water vapor and ice particles were erupting from cracks near the South Pole, shooting material so high that it was feeding Saturn's earring. This wasn't supposed to be possible. Small moons are supposed to be geologically dead, their interiors long frozen solid. Enceladus was breaking every rule we thought we understood about planetary science. The discovery sparked an immediate question. Where was all that water coming from? You can't just spray hundreds of kilograms of material into space every second without a source. The only explanation that fit the data was shocking. Beneath that frozen crust, Enceladus was hiding a global ocean of liquid water. Not puddles. Not ice. An actual ocean, potentially tens of kilometers deep, sitting in direct contact with a rocky core. That alone would make Enceladus remarkable, but what happened next pushed it into an entirely different category. Scientists didn't just detect water in those plumes. They found organic molecules, the carbon-based building blocks that life as we know it requires. Then they found salts, suggesting the ocean was interacting chemically with rock below. Then hydrogen gas, a potential energy source for microbial life. Then silica particles that could only form under very specific hydrothermal conditions. Each new measurement added another piece to a puzzle that was starting to look disturbingly biological. Think about what this means for a moment. Every single ingredient we consider essential for life, water, organic chemistry, energy sources, and mineral-rich environments, exists right now on a moon that's barely larger than some asteroids. We're not speculating about ancient conditions that might have existed billions of years ago. We're talking about an active, chemically rich ocean that's being sampled in real time as Enceladus conveniently sprays its contents into space where our instruments can analyze them. The implications hit differently when you understand how rare this combination actually is. Mars probably had water billions of years ago, but it's mostly gone now. Europa definitely has an ocean, but it's trapped beneath kilometers of solid ice with no easy way to sample it. Titan has lakes and rivers, but they're made of liquid methane at temperatures where water is harder than granite. Enceladus is the only place in the solar system where we've found all the right conditions actively operating and accessible for study, all at the same time. But here's where the story gets genuinely strange. The more we learned about Enceladus, the less sense it made. This moon should be frozen solid, a dead chunk of ice that stopped being interesting billions of years ago. Its small size means it should have lost its internal heat almost immediately after formation. There's no large planet nearby generating tidal forces strong enough to keep it warm. By every conventional model, Enceladus should look like our own moon, cold, cratered, and utterly lifeless. Instead, it's one of the most geologically active bodies we've ever discovered. Something is pumping enormous amounts of energy into this tiny world, enough to maintain a liquid ocean and power those dramatic plumes. For years, scientists assumed tidal heating from Saturn must be responsible. As Enceladus orbits, Saturn's gravity flexes and squeezes it, converting that mechanical stress into heat through friction. It's the same process that keeps Jupiter's moon Io volcanically active. The math seemed to work, barely, though it required some generous assumptions about the moon's interior structure. Then in 2014, measurements from Cassini's final close flybys revealed something that made those calculations fall apart. The amount of heat coming from Enceladus was far higher than tidal forces alone could explain. We're talking about 10 times more energy than the models predicted. That's not a small discrepancy you can explain away with measurement error. That's a fundamental problem requiring a completely different explanation, one that scientists are still actively debating. Several competing theories have emerged, each more interesting than the last. Some researchers think the moon's core might contain radioactive elements generating heat through decay, though that doesn't fully explain the localized heating near the South Pole. Others propose that the ocean itself might be chemically active, with reactions between water and rock producing heat along with those hydrogen molecules we detected. A few scientists have even suggested that tidal forces might be working in unexpected ways, perhaps amplified by the specific structure of Enceladus's interior in ways we don't yet understand. What makes this mystery particularly compelling is what it means for life. If conventional tidal heating can't explain Enceladus's energy budget, and if chemical reactions in the ocean are contributing significantly to that heat, then we're looking at an environment that's not just potentially habitable but actively energetic. Life needs energy. The more energy available, the more complex the chemistry that becomes possible. Earth's deep-sea hydrothermal vents, powered by similar chemical reactions, support entire ecosystems in complete darkness. Could something similar exist on Enceladus? The chemistry we've detected in those plumes keeps pointing in that direction. In 2018, complex organic molecules were identified, including compounds with chains of carbon atoms that on Earth are typically associated with biological processes. These weren't simple molecules like methane. We found materials like benzene and other aromatic hydrocarbons, structures that require specific conditions to form. While these can be produced through non-biological chemistry, their presence alongside water, salts, and hydrogen creates what astrobiologists call a biosignature ensemble, a collection of indicators that together become harder to explain without invoking life. Then came the phosphorus discovery in 2023, announced just months ago. Phosphorus is the final piece of the puzzle, the last major element required for life as we know it that we hadn't yet confirmed on Enceladus. It's essential for DNA, for cell membranes, for the energy-carrying molecules that power every living thing on Earth. Finding it in Enceladus's ocean, in a form that's accessible and reactive, meant that every single chemical requirement for life was now confirmed. Not theoretically possible. Actually present, measured, verified. Scientists don't use the word proven lightly when it comes to extraterrestrial life, and for good reason. Detecting the chemical ingredients for life isn't the same as detecting life itself. You can have all the right components without ever assembling them into something living. Earth's early oceans probably contained everything necessary for life for millions of years before the first organisms actually emerged. Chemistry alone doesn't equal biology. But the case for Enceladus keeps getting stronger in ways that go beyond simple chemical inventories. The plume composition varies over time, suggesting active processes in the ocean below rather than just static chemistry. The heat distribution across the South Pole shows patterns consistent with active hydrothermal systems. The very existence of those tiger-stripe fractures, the cracks from which the plumes emerge, implies ongoing geological activity driven by forces we're still trying to understand. Each observation adds another layer of complexity, another hint that something more than simple chemistry might be happening beneath that ice. What we're really talking about is probability. How likely is it that an environment with liquid water, organic molecules, energy sources, minerals, and chemical disequilibrium would remain sterile? On Earth, life appears almost immediately wherever these conditions exist. We find organisms in boiling acid pools, in frozen Antarctic lakes, kilometers deep in solid rock, anywhere liquid water touches chemistry and energy. The assumption that Earth is somehow special, that life only emerged here despite similar conditions existing elsewhere, requires increasingly creative explanations. The scientific community is being careful, as it should be. Extraordinary claims require extraordinary evidence, and detecting actual life on Enceladus would be the most extraordinary claim in human history. We need direct measurements, not just circumstantial evidence. We need to actually sample that ocean in ways that can definitively distinguish biological from non-biological chemistry. We need missions specifically designed to search for life, not just general reconnaissance flybys analyzing whatever happens to drift through the plumes. Those missions are coming. NASA and ESA both have proposals for Enceladus-focused spacecraft that would do more than just fly past. They'd orbit the Moon, sampling the plumes repeatedly with instruments specifically designed to detect biosignatures. They'd map the surface in detail, looking for the best places to eventually land. Some designs even include penetrators that could punch through the ice to sample the ocean directly, though that technology is still being developed. The political and funding challenges are real, but the scientific justification has never been stronger. Because here's what makes Enceladus different from every other target in the search for life. We don't need to dig. We don't need to drill through kilometers of ice or land in some specific location and hope we got lucky. The Moon is literally handing us samples, spraying its ocean into space where we can collect and analyze them. It's the easiest astrobiological target in the solar system, if we're willing to go there with the right tools. The implications extend far beyond one small moon. If we find life on Enceladus, if we confirm that biology emerged independently in a completely different environment from Earth, it changes everything we think we know about life's prevalence in the universe. It would mean that given the right conditions, life isn't rare. It isn't a miracle. It's almost inevitable, a natural consequence of chemistry and physics operating under certain parameters. And if those conditions exist on a tiny moon orbiting Saturn, How many other places in our galaxy might harbor life we never imagined possible? The universe suddenly becomes less lonely, less special, less centered on Earth as the one place where the cosmic lottery paid off. And that realization, that fundamental shift in perspective, might matter more than any individual discovery. But before we get too far ahead, we need to understand what we're actually looking for. The word life gets thrown around as if it has one clear meaning, but the reality is far more complex. When scientists talk about detecting life on Enceladus, they're not imagining fish swimming in dark oceans or forests of alien kelp. They're thinking about chemistry that behaves in ways non-living chemistry doesn't. They're looking for patterns, disequilibrium, organization that requires explanation beyond simple physics. The challenge is distinguishing biological signatures from clever geology. Earth's history is full of examples where scientists thought they'd found ancient life, only to discover later that minerals and chemical reactions could produce similar structures. Meteorites have arrived on Earth containing organic molecules that looked suspiciously biological until detailed analysis revealed purely abiotic origins. Mars has rock formations that resemble stromatolites, those layered structures built by microbes, except they're probably just weathered sediment. The universe is surprisingly good at mimicking life without actually being alive. So what would constitute genuine evidence? The gold standard would be finding cells, actual membrane-bound structures with internal organization distinct from their environment. But even that has complications. Would alien cells look like Earth cells? Would they have membranes made of lipids, or something completely different? Would they be large enough to see, or so small they'd slip through our filters? We're designing detection systems based on the one example of life we know, which might be like trying to recognize all possible music by only ever hearing jazz. Chemical signatures offer more immediate possibilities. Life on Earth produces characteristic ratios of molecules that don't occur in non-living systems. Amino acids, the building blocks of proteins, come in left-handed and right-handed versions that are mirror images of each other. Non-biological processes produce equal amounts of both. Earth life uses exclusively left-handed amino acids, a quirk of our biochemistry that creates an obvious signature. If Enceladus samples show similar homochirality, similar preference for one molecular form over another, that's hard to explain without biology. Isotope ratios provide another line of evidence. Living organisms preferentially use lighter isotopes in their metabolism because they're slightly easier to move around chemically. This creates distinctive patterns in carbon, nitrogen, and sulfur isotopes that differ from non-biological distributions. We can measure these ratios with extraordinary precision, looking for the subtle skewing that life produces. The trick is proving that what we're measuring reflects biology rather than some unknown geological process that just happens to produce similar patterns. Energy metabolism leaves traces too. Life on Earth operates far from chemical equilibrium, constantly pumping electrons through molecular machinery to extract energy. This creates specific chemical gradients, particular molecules that shouldn't coexist in stable environments but do because organisms are actively maintaining them. Finding these disequilibrium signatures in Enceladus samples would be suggestive, though not definitive without understanding the full geochemical context. The ideal scenario involves multiple independent lines of evidence converging. Not just one suspicious molecule, but a whole suite of measurements that collectively make more sense with biology than without. Homochiral amino acids plus isotope fractionation plus disequilibrium chemistry plus organized structures plus something we haven't even thought of yet. The more ways the evidence points in the same direction, the harder it becomes to construct alternative explanations. Current technology can't quite get us there. Cassini's instruments, remarkable as they were, weren't designed for life detection. They measured what was in the plumes at a general level, identifying broad chemical categories rather than the specific molecular details that would reveal biological signatures. It's like knowing a building contains organic compounds versus being able to read the individual books in its library. We need the equivalent of those books, the fine details that only purpose-built instruments can provide. Those instruments exist, at least in prototype form. Mass spectrometers sensitive enough to detect individual molecules at parts per trillion concentrations. Microscopes that can image structures smaller than the wavelength of light. DNA sequencers adapted for potential alien biochemistry, though that assumes alien life uses something like DNA, which is far from certain. The technology for rigorous life detection isn't science fiction. It's engineering and funding. The real constraint is getting that technology to Enceladus. Saturn orbits nearly 1.5 billion kilometers from Earth, requiring years of flight time even with gravitational assists from other planets. The radiation environment around Saturn is harsh, degrading electronics and requiring heavy shielding that adds mass and cost. Landing on Enceladus, or even achieving a stable orbit around it, demands propulsion systems and guidance precision we've only recently developed. Every kilogram of scientific instruments requires additional kilograms of fuel, structure, power, and communication equipment. Mission designers face brutal trade-offs. Do you maximize the number of plume passes with simpler instruments, or do you make fewer passes with more sophisticated equipment? Do you focus on chemical analysis, or invest in imaging systems that might spot surface features indicating subsurface activity? Do you design for flexibility, able to adapt to unexpected discoveries, or optimize for specific measurements with less margin for surprise? There's no perfect answer, only different gambles about what matters most. One proposed approach is the orbiter concept, a spacecraft that would spend years circling Enceladus, passing through the plumes dozens of times with instruments specifically designed for biosignature detection. Each pass samples different parts of the plume under different conditions, building up statistical confidence about what's actually there versus contamination or instrument error. The spacecraft would also map the surface in unprecedented detail, identifying patterns in the ice that might reveal circulation patterns in the ocean below. Another approach is more ambitious, a lander that would touch down near the tiger stripes, directly in the path of the plumes as they erupt. This eliminates the need for high-speed sampling, allowing more time for detailed analysis of fresh material before it's altered by space radiation or surface chemistry. The lander could also drill or melt through surface ice, looking for organic materials that might have frozen out of the plumes over time. The technical challenges are enormous, but the scientific payoff could be transformative. The most aggressive proposals involve actual ocean access, penetrators that would punch through the ice to sample the water directly. This is decades away technologically, requiring not just the ability to get through potentially 20 kilometers of ice, but to survive the pressure, communicate through that much solid material and operate in a completely dark ocean with no GPS, no external power source, and no possibility of retrieval if something goes wrong. It's the kind of challenge that makes Mars sample return look straightforward. Cost is the other reality. Cassini's entire mission, from development through operations, ran about $3 billion. A dedicated Enceladus life detection mission would likely cost similar amounts or more, depending on complexity. That's money competing with dozens of other scientific priorities, from exoplanet observations to particle physics to climate monitoring. The political process of allocating those resources involves scientific merit but also timing, advocacy, public interest, and sometimes factors that have nothing to do with the science itself. Yet something is shifting in how seriously the scientific establishment takes Enceladus. When Cassini first revealed those plumes, the reaction was fascination but also caution. Now major space agencies are actively planning follow-up missions. Papers on Enceladus biology appear in top-tier journals. Astrobiologists who once focused exclusively on Mars are redirecting attention to icy moons. The evidence has reached a threshold where ignoring Enceladus feels harder to justify than investigating it. Part of this shift comes from parallel discoveries about life on Earth. The more we explore extreme environments here, the more we realize how adaptable life actually is. Organisms don't just tolerate extreme conditions, they thrive in them, sometimes growing better under pressure or in darkness than in supposedly optimal environments. We've found ecosystems kilometers underground powered entirely by chemical energy from rocks, no sunlight required. We've discovered microbes that reproduce in boiling acid, in Antarctic ice, in the cooling water of nuclear reactors. The boundaries of where life can exist keep expanding every time we look. These discoveries aren't just academic curiosities. They directly inform what we should expect on Enceladus. If Earth life can survive in environments that superficially resemble that subsurface ocean, environments with similar chemistry and energy sources and physical conditions, then the argument that Enceladus is too extreme for biology becomes much harder to sustain. The question shifts from whether life could exist there to whether it actually does, which is a very different kind of uncertainty. Human summary. One way to think about this is through probability layering. The chances that any single piece of evidence points to life might be small. But when you stack independent lines of evidence, the cumulative probability shifts. Enceladus has liquid water, confirmed. It has organic molecules, confirmed. It has energy sources in the form of chemical disequilibrium, strongly indicated. It has the right pH range based on plume chemistry. It has a rocky core providing minerals and catalytic surfaces. Each of these alone is interesting. Together, they describe an environment that looks increasingly similar to places on Earth where life not only exists but dominates. This doesn't prove biology. It does mean the null hypothesis, the assumption that Enceladus is sterile, requires stronger justification than it once did. You can't simply point to the cold or the darkness or the isolation and declare life impossible when we found terrestrial organisms thriving under all those conditions. The burden of proof hasn't fully reversed, but it's definitely shifting. There's also a philosophical dimension here that scientists don't always articulate but definitely think about. If we find life on Enceladus, it answers one of the oldest questions humans have ever asked. If we don't find it despite those conditions being right, that tells us something almost as important. It means the origin of life is harder than we thought, that even with all the right ingredients, biology doesn't just spontaneously emerge. Either outcome fundamentally changes how we understand our place in the universe. That's why some researchers push so hard for this mission despite the cost and complexity. It's not just curiosity, though that's part of it. It's the recognition that opportunities like this are rare. We've explored dozens of worlds and found exactly one with confirmed life. Now we have a second candidate that's actually accessible, that's literally spraying its ocean into space for us to sample. Walking away from that because it's expensive or difficult feels like a choice future generations would struggle to understand. The detection strategy matters as much as the mission design. What exactly would constitute proof of life in those plumes? This isn't as straightforward as it sounds. Organic molecules alone won't cut it. We've already found those, and they could easily form through non-biological chemistry. Simple amino acids, the building blocks of proteins, exist in meteorites that have never been near life. Even complex organics can emerge from purely chemical processes given the right conditions and enough time. The gold standard would be something that screams biology, something chemistry alone can't easily explain. Patterns in how molecules are arranged. Life on Earth shows strong preferences, or chirality, in molecular structure. Amino acids come in left-handed and right-handed forms that are mirror images. Terrestrial biology almost exclusively uses left-handed amino acids. If Enceladus samples showed a similar bias, that would be striking because random chemistry produces equal amounts of both. A strong imbalance suggests selection, and selection usually means biology. Another marker would be isotopic ratios. Living organisms preferentially use lighter isotopes of elements like carbon and nitrogen because they're slightly easier to incorporate into biochemical reactions. This leaves a measurable signature, a deviation from what you'd expect in non-biological material. Multiple measurements showing consistent isotopic fractionation across different molecules would be hard to explain without invoking life. Then there are structural signatures. Cell membranes, even if the cells themselves are destroyed during sampling, might leave behind lipid patterns or vesicular structures visible under microscopy. Polymers with repeating units, especially if they show sequence complexity rather than random repetition, would raise serious questions. Biology builds information-rich structures. Chemistry builds repetitive or random ones. Spotting that difference requires incredibly sensitive instruments and careful analysis, but it's doable. The challenge is that we're looking for life that might not resemble Earth biology at all. It probably uses the same basic chemistry, water and carbon and energy flow, but the details could be wildly different. Maybe it doesn't use DNA. Maybe its proteins are built from different amino acids. Maybe it has cell walls made of materials we've never seen in terrestrial organisms. Designing instruments that can detect life as we know it while remaining open to life as we don't know it is one of the hardest problems in astrobiology. This is where contamination becomes a nightmare scenario. If we send a spacecraft that isn't perfectly sterilized and it finds organic molecules, how do we know they're not hitchhikers from Earth? Cassini wasn't built with biology in mind, so its cleanliness standards were lower than what we'd need now. Any future mission would require planetary protection protocols far more stringent than anything Cassini followed. That means building the spacecraft in ultra-clean facilities, sterilizing components with heat or radiation, and proving through rigorous testing that contamination levels are below detection thresholds. Even then, interpretation will be contentious. Science operates on reproducibility and peer review. One measurement showing possible biosignatures won't be enough. We'd need multiple independent detections, ideally using different techniques. We'd need ground-based labs analyzing return samples, if we can manage that technologically. We'd need theoretical models explaining how those signatures could arise biologically and why they couldn't arise chemically. The bar for claiming discovery of extraterrestrial life is extraordinarily high, as it should be. But here's what makes Enceladus different from every other target in astrobiology. The ocean is sampling itself. We don't have to drill through kilometers of ice or land on a hostile surface or wait decades for a rover to reach the right location. The plumes bring ocean material directly to us, fresh and uncontaminated by surface processes. That accessibility is transformative. It means the first real test of whether a subsurface ocean harbors life could happen within our lifetimes, maybe within the next 20 years if funding and planning align. Compare that timeline to Europa, where we're still debating whether we can even confirm the ocean's existence from orbit before committing to a lander. Or Titan, where the interesting chemistry is happening in lakes of liquid methane at 90 degrees above absolute zero, requiring entirely different instrument designs. Or Mars, where we've been searching for decades and still haven't found anything definitive despite constant presence on the surface. Enceladus offers a shortcut, a way to answer the life question without solving all the intermediate technical problems first. The geopolitical aspect is less discussed but increasingly relevant. Space exploration has always involved international cooperation and competition in varying measures. Right now, NASA is leading most serious Enceladus mission concepts, but ESA, the European Space Agency, has expressed strong interest in collaborative efforts. China's space program is expanding rapidly and has mentioned icy moon missions in long-term planning documents. Russia, despite economic constraints, maintains significant expertise in planetary science. A discovery of life on Enceladus wouldn't belong to any single nation. The scientific data would be shared globally, analyzed by researchers across dozens of countries, debated in international conferences and journals. But the prestige of making that discovery, of being the agency that sent the spacecraft that found it, matters. It shapes funding priorities, inspires the next generation of scientists and engineers, and demonstrates technological capability. These factors influence which missions get approved and when. There's also the private sector angle. Companies like SpaceX have dramatically reduced launch costs, which directly affects mission feasibility. A mission that would have cost $5 billion a decade ago might now be achievable for $3 billion because getting the spacecraft off Earth is cheaper. If that trend continues, the financial barrier to ambitious outer solar system missions drops steadily. That could accelerate timelines or allow more complex mission designs than traditional budgets would support. Would commercial interests ever target Enceladus directly? Probably not for resource extraction. The distances are too vast and the energy requirements too high for any conceivable economic return. But privately funded science missions aren't impossible. Several wealthy individuals have expressed interest in astrobiology. If someone wanted to fund an Enceladus life detection mission as a legacy project, the technical capability exists. It hasn't happened yet, but the landscape is shifting in ways that make it less unthinkable than it was even 10 years ago. Public perception plays into this as well. Missions require sustained political support, which means maintaining public interest across administrations and budget cycles. Enceladus has an advantage here because the concept is simple to communicate. There's an ocean under the ice. We can sample it. We might find life. That narrative resonates in ways that more abstract science goals sometimes don't. It's concrete, visual, and tied to a fundamental question people actually care about. The media coverage of Cassini's discoveries demonstrated this. Every major plume finding made headlines. The hydrothermal vent evidence was covered by mainstream news outlets, not just science publications. That visibility matters when Congress or parliaments are deciding which missions to fund. A mission to Enceladus isn't just scientifically justified, it's a story people want to follow. Human summary. And what happens if we actually find something? Not just organic molecules or chemical signatures, but clear, unambiguous evidence of biological activity. Something living, or something that was alive recently enough that we can study its biochemistry. The protocols for that scenario exist but have never been tested in practice. NASA established planetary protection guidelines decades ago, rules designed to prevent contamination in both directions. We don't want to accidentally bring Earth microbes to another world and mistake them for indigenous life. We also don't want to bring back something from another world without proper containment, though that's less of a concern for a mission that won't return samples directly to Earth. But the scientific protocols are just the beginning. The confirmation process would be rigorous to the point of paranoia. One instrument reading wouldn't be enough. One type of measurement wouldn't be enough. The standard would require multiple independent lines of evidence, preferably from different analytical techniques, all pointing toward the same conclusion. And even then, the debate would be intense. When Viking landers conducted experiments on Mars in the 70s, one test produced results that could have indicated microbial life. Decades of argument followed. Most scientists now think it was a chemical reaction, not biology, but consensus took years to establish. With Enceladus, the scrutiny would be even more severe because the implications are so profound. Teams would need to rule out every conceivable non-biological explanation before claiming a detection. That takes time, careful analysis, and probably follow-up observations if possible. The spacecraft might need to sample the plume multiple times, looking for consistency. Are the same signatures present in different plume particles? Do they show up in the same ratios? Are there seasonal variations or do the readings remain stable? Repeatability matters enormously in science, especially when making extraordinary claims. One intriguing reading is a puzzle. 3 identical readings from separate samples start looking like a pattern. 10 readings, all consistent, all showing the same biological markers, that becomes very difficult to explain through non-biological chemistry alone. Then there's the question of announcing it. How do you tell the world that we found life beyond Earth? The process would likely involve peer review first. Scientists would prepare papers documenting every measurement, every analysis, every alternative explanation they considered and rejected. Those papers would be submitted to journals like Science or Nature, where other experts would examine the methodology in detail. Only after passing that review would there be an official announcement. That's the ideal sequence anyway. In reality, information leaks. Mission teams involve hundreds of people. Data gets shared among collaborators. Someone always talks to someone else who talks to someone else. The discovery might become an open secret in the scientific community weeks or months before any public statement. Managing that information flow, preventing premature claims while maintaining scientific integrity, would be a challenge unlike anything space agencies have faced before. Because once the news breaks, the response would be immediate and global. Media coverage would be overwhelming. Every news organization on the planet would want the story. Scientists involved in the mission would face endless interview requests. Social media would explode with speculation, excitement, skepticism, and probably a fair amount of conspiracy theorizing. Religious institutions would need to grapple with theological implications. Philosophers would debate what it means for humanity's place in the universe. Artists and writers would produce countless works inspired by the discovery. It would reshape conversations across every domain of human culture. Politically, the response would probably be unifying in the short term. Finding life elsewhere is the kind of news that transcends national boundaries and ideological divisions. It's bigger than any single country or political system. In that moment, humanity would have a shared experience, a collective realization that we're not alone, that life is a cosmic phenomenon rather than an Earth-specific accident. That could produce a brief period of global solidarity, a sense of common purpose and shared wonder. How long that lasts is another question. Humans are skilled at turning even unifying moments into sources of division. But initially, the reaction would likely be one of excitement and curiosity rather than fear or conflict. The practical questions would follow quickly though. What do we do next? One detection from one moon wouldn't tell us everything we need to know about life in the universe. It would tell us that life can exist in an ocean world beneath an ice shell. It would tell us something about the chemistry that supports it, the energy sources it uses, the environmental conditions it tolerates. But it wouldn't tell us how common life is, whether it arose independently on Enceladus or somehow shares an origin with Earth life, whether it's simple bacteria-like organisms or something more complex, whether it's currently active or represents an extinct biosphere we're detecting through molecular fossils. Each answer would generate 10 new questions. The logical next step would be more missions. If we find life on Enceladus, Europa immediately becomes a higher priority target. Does it also harbor life? Is it the same kind of life or something different? What about the other ocean worlds, Ganymede, Callisto, Titan? Do they show similar biosignatures, or is Enceladus unique? Sample return missions would move from theoretical to essential. We'd need to bring material back to Earth where it could be analyzed with laboratory equipment far more sophisticated than anything we can fit on a spacecraft. That introduces the contamination concerns again, requiring quarantine facilities and handling protocols, but the scientific payoff would be enormous. We'd want to sequence genomes if the life is DNA-based, or understand whatever information storage system it uses if it's not. We'd want to study its metabolism in detail, grow it in culture if possible, understand its evolutionary history. All of that requires samples and equipment that won't fit through space anytime soon. Then there's the long-term question of protecting these environments. If Enceladus has life, do we have an obligation to leave it undisturbed? Right now, the moon is pristine, or at least as pristine as something can be after we've flown a spacecraft through its plumes several times. But intensive study would mean more missions, more instruments, possibly even landers on the surface or submarines in the ocean eventually. Each mission carries some risk of contamination, some chance of introducing Earth organisms that could disrupt or destroy native ecosystems. Space agencies take this seriously. Spacecraft bound for potentially habitable worlds undergo intensive sterilization. Components are heated to kill any microbes. Surfaces are cleaned with harsh chemicals. Assembly happens in clean rooms with filtered air and strict protocols. Nothing is perfect though. Some microbes survive extreme conditions. Spores can endure heat, cold, radiation, and vacuum. The chance of introducing something isn't zero, it's just very low. But very low multiplied by multiple missions over decades starts to add up. International agreements would probably be necessary. Rules about how many missions are allowed, what kinds of instruments can be used, what areas are off-limits to protect pristine environments. These agreements exist in principle through the Outer Space Treaty and Planetary Protection Guidelines, but they'd need to be strengthened and made more specific if we're dealing with confirmed biospheres rather than potential ones. And enforcement becomes tricky. Who decides what's acceptable? Who has the authority to prevent a nation or organization from launching a mission if they disagree with the restrictions? Space law is still developing in these areas. We're writing the rules as we go, usually staying one step behind the technology. The other long-term consideration is what finding life on Enceladus would mean for the search elsewhere. Does it make life seem more common or less? If two places in our solar system have life, that suggests biology emerges readily when conditions are right. Water, chemistry, and energy seem to be enough. That would be encouraging for the search around other stars. Every planetary system probably has multiple ocean worlds. If ocean worlds reliably develop life, then life might be everywhere. But there's a counterargument. What if Earth life and Enceladus life share a common origin? Panspermia, the idea that life can spread between worlds through meteorite impacts, isn't impossible. Mars and Earth have exchanged rocks throughout history. Material from Earth has reached the outer solar system, though rarely. If Enceladus life turns out to be related to Earth life genetically, That would be fascinating but also disappointing in a way. It would mean we've only found one origin of life, not two. We still wouldn't know if life is common or rare. We just know it can survive in different environments once it gets started. Distinguishing between these possibilities would require detailed genetic or biochemical analysis. If Enceladus life uses the same DNA structure, the same amino acids, the same basic cellular machinery as Earth life, common origin becomes likely. If it uses different building blocks, different coding systems, different fundamental chemistry, then it almost certainly arose independently. That would be the more profound discovery, two separate origins of life in the same solar system. At that point, the universe would statistically be teeming with life. We'd just be early in the process of finding it. The discovery wouldn't just reshape our understanding of life's abundance. It would force us to confront uncomfortable questions about intelligence, consciousness, and our own significance. If simple life exists in multiple places within one solar system, what about complex life? What about intelligence? The gap between microbes and minds is enormous, but if biology gets started easily, maybe that gap gets crossed more often than we think. Or maybe not. Maybe microbial life is common but complex multicellular organisms are vanishingly rare. Birth took billions of years to move from single cells to animals. Most of that time was spent as a microbial world. Intelligence came even later, in just the last few million years, a blink in geological time. There's no guarantee that evolution trends toward complexity. Natural selection doesn't have goals. It doesn't push life up a ladder toward intelligence. It just favors whatever works in the moment. If simple works, simple persists. Enceladus might have had life for billions of years without ever developing anything more sophisticated than bacteria. That would still be remarkable, but it would also suggest intelligence is a fluke, a rare accident that happened once on Earth and maybe nowhere else nearby. Then again, we don't really know what intelligence requires. We assume it needs complexity, nervous systems, brains. But what if there are other forms of cognition we wouldn't recognize? What if microbial communities develop collective behaviors that look simple individually but show emergent properties we'd classify as intelligent if we knew what to look for? We've seen hints of this on Earth. Bacterial colonies communicate chemically, coordinate responses, make collective decisions about growth and movement. Slime molds, not even animals, can solve maze puzzles and optimize network structures. Intelligence might not require neurons. It might just require information processing, feedback loops, and environmental interaction. Enceladus life could surprise us in ways we haven't imagined yet. But even if it's just microbes, the philosophical implications cut deep. For all of human history, we've wondered if we're alone. Every religion, every culture has grappled with our place in the cosmos. Finding life elsewhere, even simple life, even in our own solar system, changes that conversation permanently. We're not unique. We're not central. We're one example among potentially countless others. Some people find that thought liberating. It removes the burden of cosmic specialness, the pressure to justify our existence through uniqueness. We're just part of a larger pattern, one thread in a vast biological tapestry. Others find it unsettling. If we're not special, what's the point? If life is common, does individual life matter less? These are emotional reactions, not logical ones, but they're real and they'll shape how society processes the discovery. The scientific community would adapt quickly. Researchers would pivot to new questions, new investigations, new grant proposals. But the general public moves slower. Cultural narratives take time to shift. Education systems would need to incorporate this new reality. Textbooks would be rewritten. Documentaries would be produced. Children would grow up in a world where extraterrestrial life isn't science fiction, it's established fact. That generation would see the universe differently than any before them. They'd assume life is normal, expected, something to be studied and understood rather than wondered about in the abstract. Their questions would be different. Not whether life exists elsewhere, but what forms it takes, how it works, whether we can communicate with it. The long-term trajectory of human civilization might shift. If we know life is out there, space exploration becomes more urgent. Not just for scientific curiosity, but for connection, for understanding, for the possibility of finding something beyond microbes. Investment in telescopes, spacecraft, and astrobiology would increase. Private companies would get involved, not just governments. The economics of space would change if there's something genuinely valuable to find, not just rocks and radiation. And valuable doesn't necessarily mean resources. Knowledge is valuable. Contact is valuable. Understanding our place in a living universe is valuable in ways that don't show up on a balance sheet. But practical concerns would emerge too. If we're visiting Enceladus regularly, someone will eventually propose mining it. The moon has water, organic compounds, energy. Those are useful. Future spacecraft could refuel there. Habitats could be built. Humans might want to establish a presence. That raises a collision between exploration and exploitation. Do we have the right to industrialize a world with native life? Even if that life is microbial? Even if it's confined to subsurface oceans we're not directly disturbing? There's no clear answer. Earth's history offers cautionary tales. Every time humans encountered new ecosystems, we disrupted them. Sometimes deliberately, sometimes accidentally, but always irreversibly. Islands, forests, oceans, we've left marks everywhere. Doing the same thing on Enceladus would be consistent with our track record, but knowing we're doing it makes the choice more conscious, more morally weighted. Some would argue life anywhere is precious and must be protected absolutely. Enceladus should be declared a nature preserve, off-limits to anything beyond minimal scientific study. Others would argue humans have needs too, and resources in space should be available for our use, especially if that use enables further exploration and the spread of Earth life to new environments. Finding balance between these positions would require international cooperation on a scale we've rarely achieved. The Antarctic Treaty System provides a model. Antarctica is protected for scientific research, with resource extraction banned. Military activity is prohibited. Multiple nations cooperate to maintain the agreement despite political differences elsewhere. Something similar could work for Enceladus, but enforcement is harder when you're dealing with space. There's no border patrol in the outer solar system. Monitoring compliance would require trust, transparency, and shared oversight. Violations would be difficult to detect and even harder to punish. Still, the attempt would be worth making. Establishing norms now, before economic interests become entrenched, is easier than trying to impose rules later. The discovery of life on Enceladus would give us that narrow window, that brief moment when everyone agrees protection matters before anyone has invested billions in infrastructure. That window wouldn't stay open long. Within a decade, maybe two, commercial interests would start pushing boundaries. Technology would advance. Costs would drop. The moon would go from distant curiosity to accessible destination. Once that transition happens, preservation becomes much harder. So the discovery itself would trigger a race, not just to study Enceladus, but to define its future. Scientists racing to gather data before environments are disturbed. Ethicists racing to establish guidelines before they're needed. Policymakers racing to create enforceable frameworks before violations occur. And entrepreneurs racing to figure out what can be extracted, sold, or utilized before regulations lock things down. All of this would unfold in parallel with continued searching elsewhere. Because if Enceladus has life, the next question is immediate. What about Europa? What about Titan? What about the moons of Uranus and Neptune we've barely studied? What about ocean worlds around other stars? The search would expand rapidly, driven by the knowledge that we're not looking for something hypothetical anymore. We're looking for variations on a theme we've already confirmed. That's a different kind of search, more concrete, more urgent. Funding would flow toward missions that can answer these questions. Public support would be strong. Media coverage would be intense. The field of astrobiology would transform from speculative science to mainstream research with clear goals and measurable progress. Universities would expand programs. Students would flood into the discipline. The best minds of a generation would focus on understanding life beyond Earth, how it starts, how it evolves, what forms it can take. Within a few decades, we might have a comparative biology that spans multiple worlds. We'd understand what features are universal and what varies. We'd know if DNA is inevitable or just one option among many. We'd see if evolution follows similar patterns everywhere or takes wildly different paths depending on environment. That knowledge would feed back into our understanding of Earth life. We'd see ourselves more clearly by seeing what we're not. The assumptions we make because we only have one example would become visible. We'd recognize which aspects of biology are fundamental and which are accidents of our particular history. And somewhere in that process, the question would surface again, sharper than before. If simple life is common, what about complex life? What about intelligence? What about civilizations? Are we alone in that category, or is the universe filled with minds looking outward just like we are, wondering the same things? the question shifts from whether we're alone to whether we're typical. And that distinction matters more than it seems at first. Being alone means something fundamentally different than being rare. Being rare but not unique means the path we took, from chemistry to cells to consciousness, can happen elsewhere given enough time and the right conditions. That would make intelligence not a miracle but a statistical outcome, improbable for any single world but inevitable across enough worlds. The discovery of microbes on Enceladus wouldn't answer that question directly. Simple life doesn't predict complex life. Earth had bacteria for billions of years before anything more complicated emerged. The jump from single cells to multicellular organisms required specific conditions, particular evolutionary pressures, maybe a dose of luck. Nothing about finding bacteria on Enceladus would tell us if that jump is easy or nearly impossible. But it would narrow the possibilities. Right now, we can't rule out the idea that life itself is the bottleneck, that getting from chemistry to biology is so difficult it only happened once in the observable universe. Finding life on Enceladus would eliminate that possibility. The bottleneck would have to be somewhere else, either in the transition to complexity or in the emergence of intelligence or in the development of technology. Each of those could be common or vanishingly rare. We don't know. We can't know from a single data point. But we'd know more than we do now. We'd know the first step isn't impossibly hard. And that would shift how we think about the rest of the ladder. If microbial life turns out to be common, scattered across ocean worlds and buried in subsurface environments throughout the galaxy, then the question becomes duration. How long does life need to develop complexity? Earth took about 3.5 billion years to go from bacteria to animals. Is that typical?